Well, thank you for having me, and I'm here so that I can do a dry run for the talk that I'm doing in Adelaide. And I've simplified my slides as much as possible, and like feedback where things seem a little gnarly or uncomprehensible. So you can go to the next slide. I have been working with the fellows. Okay, so I'm going to go through this as an agenda: background and analysis of existing definitions, different perspectives and worldviews, developing an integrative model, and then a summary in our next steps. So a team of fellows were put together. Go ahead, go to the next one. In the fellows discussion groups, there's this constant dialogue about different topics. Same thing with the systems science working group. Some of it very philosophical, some of it quite interesting. And so after just a train of these discussions amongst the fellows, our chair, Dorothy, suggested that we put together a team, and we subsequently got together with the president of INCOSE. And we were chartered with the notion of revisiting a definition for systems and systems engineering. And the reasoning behind that is basically our vision and mission for INCOSE has changed in the last 5 years. And if you guys aren't familiar with the 2025, the Vision 2025, which is a world-class product that was put out and was a very good idea of where we're going with systems engineering. So with that motivation, our president said that it would be good for us to do this again, to revisit it and see if we can change it as part of our INCOSE vernacular. And so our approach was to basically go through a bunch of definitions of system and then use some of the soft systems methodology. There were two other efforts where they use soft systems methodology. And if you guys don't know Checkland, he is the guru of soft systems methodology. I think he's in Denmark or Sweden. And the way they develop systems there are really about engaging the community, engaging stakeholders. And he is one of our pioneers, Checkland is. And they've used that method, and I actually reference his work a lot in my dissertation work because he's just really good in the elicitation and trying to understand the problem at hand. But the architecture group used this methodology as well as a group that was studying capability to try to understand definitions where people struggle, and then we were going to propose a set of definitions. We pretty much figured out that we weren't going to be able to come up with the one definitive definition. And so our vision is basically to develop a definition or a set of definitions that begin to bring communication together and to allow us to be able to interact with other organizations that think about systems but maybe not in the way we do. And then also just from an INCOSE specific is to align it better with our 2020 vision. Some of the key discoveries, and this is the executive summary, there are many valid and different worldviews about systems. And I'm going to talk a little bit about the worldviews that we came up with. And there's at least 5 that we found that I'll talk about. And then, so it's basically, we figured out and we sort of had that intuitive understanding that we weren't going to come up with one definition for system. And there really is no benefit in doing so. So we came up with a framework, notionally a topology for systems, and some key concepts associated with the different types of the system. And you'll see that we went through a lot of literature for this kind of conclusion, I guess. Go ahead. So here's the definition in the INCOSE handbook, version 4. So basically, if you look at those definitions from the handbook, you'll notice that and it's a function of who we are as systems engineers and how we've evolved, is that we're looking at real systems that are human engineered for the most part, and that they have defined environments. Because if you think about the systems engineering process, you look at the environments the system's going to be in, and your intent is to create a real system, right? So we go from that concept viewpoint. Yep, I think I covered all the concepts. So it doesn't really address natural systems, for instance, or human systems that are impinging on natural systems. It doesn't cover up systems that, for instance, have emerged. A lot of people may or may not know, but the internet as it is today was not designed from top down. And so there's emergent systems, and there's non-deterministic environments. If you think about autonomous systems these days, you're not going to be able to predict all of the environments that might occur to those autonomous systems. And then if you have autonomous systems interacting with autonomous systems, or non-autonomous systems, let's just say, I mean, think about when we finally introduced autonomous cars in the environment, and you have human drivers in regular cars and bicyclists, and so you start to think about those environments, and you're not going to be able to conclusively come up with all the environments that could potentially face. Are you ready to switch over?
Yeah. When I asked Rick if he can email me your slides,
oh, okay.
I have those.
So let's move on to the next slide. So in trying to address this, you know, the Vision 2025 suggests we need to address a wider scope. If you look at the 2025, it's really all about what challenges as humanity do we face, and where are we going with these challenges from a systems perspective, and certainly a systems engineer, what's systems engineering role in all of that. So talks about natural and resource management systems, finance and insurance systems, ecological systems, social systems, which we understand enterprises. INCOSE had the systems engineering journal for many years, but then we introduced the one on enterprise, and that was a really good addition. So we're thinking larger, and if you think Stevens Institute is, you know, they're in the College of Systems and Enterprises, you know, so that's a form of social systems. And then, and so not all parts of these systems are human-made or human-specified, obviously, right? And we believe as fellows, and we assert that any use of the word purpose, because we always talk about what's the purpose of your system, is a human-made concept. You know, if you think about natural systems, we attribute purpose. Do they really say my purpose is, you know? And so, and many times it's really associated with the human purpose. And then it is not sufficient to design these kinds of systems to work in a defined environment, and that starts to change the way we think as systems engineers. And in particular, if you try to sort of propagate the notion of systems engineering outward to many engineering disciplines, because unfortunately still today, chemical engineers, mechanical engineers, electrical engineers don't come out of school with a basic understanding of systems engineering. And they define and build widgets with a very narrow aperture on everything they might affect, and the causal and the unintended. And so that's part of what we, as a leadership organization, should be thinking about, is that what do we want to propagate into the future as, you know, as citizens, as systems engineers, and certainly in the leadership roles that we hold. Some of the things to think about is that we do have to figure out where non-determinism comes in. We have to at least not have our eyes closed to that, you know. And then we also need to understand, and years and years ago, I took a class on the notion of graceful degradation and how you create a system that is robust and all that kind of stuff. I want to say 1985 at UNM. I have a book that is out of print that I still leaf through because it's such a great topic. But thinking about how systems degrade, and not just the systems that we create, but how they degrade in a system of systems context gracefully, you know. And it is a difficult challenge. You can go on to the next one.
This is a dry run, you said. I think the last bullet is be more clear.
Okay.
We are able to design for these kinds, or I'm not sure what we're.
Okay, thank you. Did I have a pen? I had a pen. Okay.
I'm trying to get the slides.
Yeah, particularly as they get more complex, you find them the next one after this one, for instance. So, of course, what you go back to is etymology. We kept mixing it up as well. Is what's the origins of words, right? You know, it's always worthwhile to revisit that. And the notion of system goes back etymology. Yeah, they're a pretty good, complex system if you think about it. Is to, you know, the notion of from the sun meaning with, and histani meaning to cause to stand. So the idea is to standing together, togetherness. And, you know, it was in Sanskrit early on in our understanding as humans, looking at the world around us. You got it?
Yep. It's going to take me a few seconds.
Okay, I apologize. We're going to do a switch over to PowerPoint only because, especially in the next slide, there's some animation. So there's some schools of thought and systems. So you start back, go ahead and hit the next thing. And unfortunately, I can't read the slide. So you start back and as early as, what, 300 BC? I can't see very well.
384.
384, I better go closer. If I can't read my slides, then I can't read this. I apologize. Yeah, 384 through 22 BC. The whole is something over and above the parts, and not just the sum of the parts. And I think one of the things about these things, and people thinking about these things for years and years and years, is that we sort of take these things for granted, of course, where we're at today. But in that day, that was a breakthrough. That, you know, there's this notion of synergistic parts working together to achieve some greater good or greater set of properties. And then reductionism, which is what we do, divide and conquer, breaking an architecture into subsystems. That's reductionist approaches are fostered for rapid progress in experimental physics and biology and medicine. And then the concept of the system evident in the work of thermodynamics. So other areas that were very much around, and that's one of the things that when we were exploring definitions, we also looked at domain-specific definitions. You know, for instance, you know, civil engineering or aerospace engineering, and there's definitions that we sort of garnered from there as well. And then extended Carnot's work added the concept of environment. In other words, a system exists within an environment. Go ahead, go to the next one. And then Bertalanffy, which is what a lot of the basis of what we have defined here is based on Bertalanffy, general systems theory work. And I'll just do a little side note here. One of the things that INCOSE has is they have a relationship, an MOU with the International Systems Science Society. And they bring to bear a lot of the very fundamental philosophical concepts around systems. And Bertalanffy is one of the people that underpins a lot of the work that they're doing. There's still not a notion of a general systems theory. They're peeling it apart, they're looking at a lot of different things, but there's really not truly a general systems concept. We're building it. And then Gödel, Turing, and Shannon, which hopefully those names are somewhat familiar to you. Shannon's information theory, Turing's machine. And so that's the advent of theoretical computer science, which is was a breakthrough in thinking about systems, especially on the conceptual side. Go to the next one. So then some of the follow-on, cybernetics, which, there's tons of conferences on cybernetics. Miller, which is the living systems work, a lot of living systems work. And then complex adaptive systems, which many of you guys may have heard about the complex systems working group. And a lot of the system of systems, and they kind of overlap a little bit, but the notion of complex adaptive systems is something that's relatively recent if you think about it. And then systems in management, and this is where some of the soft systems thinking, they're relatively the same time frame, beginning about the mid-'80s and on. And systems thinking, and then Forrester's system dynamics work. Go ahead to the next slide. And of course, part of this branch became systems engineering. I think the first systems engineering textbook was written around 1965 time frame, and then of course it's built from there. Go ahead. It just explains reductionism in case many of you guys, I'm sure people in here understand the concept of reductionism. So we compiled words, and we had to take multiple tries at this. One of the things is anytime you have a definition, don't have the word that you're trying to define in the definition, because then you get it at large as life. But if you think about it, some of this is very intuitive. So we took 100 definitions, parts, whole, elements, properties, group, organized, together, components, interrelatedness, network. So those are some of the words that pop out, which are words that many people probably in here can relate to. But there's many, many definitions out there in the world, and a lot of them parallelize each other. Go to the next one, and I'll show a slide on that. But here's some interesting dichotomies about the definition of system. The notion of systemic versus systematic. Okay? Think about those two words. Artificial versus natural, and the notion of hybrid or both. And again, because we mine definitions even from other domains, real world and corresponding formal systems. So formal systems, for instance, we have the notion of the system of mathematics, right? That's a formal system. If any of you guys have designed compilers, that's all axiomatic semantics. That's a formal system. Real world versus mental models, mental constructs. Whole versus parts. And then structure versus behavior and or behavior. Purpose or not, which we just talked about. And then the notion of fitness for purpose. So if you exclude the notion of purpose, then something fitness of purpose. Do those two things, are they exclusive of each other? And then persistence, resilience, or for naturally occurring and designed systems. We're thinking about resilience a lot in the world today, in our systems world today, particularly for things like mission assurance, our infrastructure, power infrastructure, et cetera. And then holistic versus reductionist, which are really, if you've ever taken any kind of systems thinking courses, you'll understand that one of the things that you do in systems thinking is actually put on one hat, try to look at it from that viewpoint, see what you discover, take that hat off, put another hat. And so you can look at things both holistically and reductionistically, but keep in mind that either or is probably incomplete. And then general versus domain specific. And, basically we're still trying to come up with a nirvana of general systems theory. A lot of times it's very hard, and people like Dinesh Verma has said, systems engineering without an application domain is sterile. It's something that, and it's an application, by definition, systems engineering is an application engineering, an engineering that you have to apply to something, some domain. Another interesting word is the notion of systemness. And it really relates to the capacity of system to manage itself and react in the face of changing, unstable environment. If you think about who we are as systems in the world, people, and how we can react to the environment around us. as we go forward in engineering systems and systems of systems, even enterprises, that notion of your capacity to manage itself in a and I'm adding this, and react to changing environments, and hopefully in a way that creates resilience and longevity. And those are the kinds of things that you like to think about systems. I'm trying to think if there's anything else I really want to bring up. Go ahead. So this next slide I love, because what it did, it condensed a lot of the definitions. And you'll notice that basically there was a framework for it. A system is a set, combination, group, collection, configuration, arrangement, or organization, ensemble. And think of this, think of the Hoover Dam in the midst of the Las Vegas desert, or that area over there, Parts of parts, components, elements, objects, systems, entities, combined, integrated, organized, configured, or arranged in a way that creates, enables, motivates properties, functions, processes, capabilities, behaviors, dimensions, not possessed or exhibited or presented by the separate individual single parts, components, elements, objects, subsystems, entities. And you will see that the reason why there's so many words here as we go on, that the typology, because we're considering conceptual systems as well as real systems. And we're considering multiple kinds of real systems and multiple kinds of conceptual systems. Let's go on. So, what are the different perspectives and worldviews? To start with, I'd like to, one of the things we did was we created, based on all of this research of the definitions of systems, we created a survey. And we had on the order of 25 fellows take the survey. We refined it, and then we put it out to this systems science working group. And the output of that was, we had sort of a working model of the worldviews that we were seeing. And I'll try to talk a little bit through that as I'm addressing these worldviews. Go ahead and go to the next one. So within our community, we deciphered basically 5 worldviews. And a worldview, and this is one of the debates that we had a lot, but in Checkland's work, he talks about the notion of a Weltanschauung, which is, if you know anything about German, it's got a lot of richness in one word like that. But Weltanschauung basically means what lens I come to the world and how I look at the world, and the filters that I put on that. And so that notion of a worldview is what Checkland tries to address, because a lot of our miscommunication, a lot of what things are missed in building systems because we don't understand what lenses people are coming at a system from. So we have 5 worldviews here, and I'll walk through each one of them. And so I won't articulate each of these here, but there's 5 worldviews, and I will go into those now. Go ahead. So the first worldview is a formal minimalistic view based on mathematics and logic. And basically this worldview holds that you cannot conceive of a real system without conceiving it conceptually first. And you can have a conceptual system without having a real system. Okay? And it comes from the world of math. Think about Einstein's grand opus, what he wanted to achieve in his lifetime, and what mathematicians have sort of proved, but we have not been able to understand yet, which is that all energy forces relate to one another. They're able to do that with math out to like the 7th or 9th figure or something like that, but there is no realized system that we understand or can develop any kind of models around that support that. And maybe that's not a great example, but math itself can come up with algorithms and stuff like that that may or may not get realized in real systems, for instance. And so if we look through this, let's see. pretty much what I want to say. Like, you know, the words itself you can relate to. It's a very interesting perspective, and it is a valid perspective, right? Okay, go to the next one. Constructivists they believe that the systems are purely a mental construct. In other words, we look out at the world and we say things are systems, but that is something that we do to explain the world, you know? So we had about 20% of both survey groups. One of the things that these group of people did sort of articulate is that when we look out on the world and call things systems, we do say that they comprise of more than one part in relationship with each other, and that there is some boundary, although many people consider that a choice where you make the boundary, and then that it exhibits some emergent properties arising from the relationships and interactions between the parts. And interestingly enough, the people that ascribe to this viewpoint don't necessarily believe that it has to have a purpose or a goal. And I guess a good example of this would be a scientist looking at the world, you know, and trying to explain the world based on just observing the world. There are conceptual systems are considered to represent parts of the real world by by definition, because that's the way we're describing it. And when we do that, we have what we call abstracted systems. So the conceptual part of that is an abstracted system. Not in this worldview is the word configurations represented by abstracted system considered to be systems. I'm not sure what that, I'm going to have to go back to remember what that was trying to get across. Sorry. Go on to the next one. What that point was. Let's see. So there was a consensus on this notion of a moderate realist, which I would guess that, I don't know, I'm a moderate realist. I don't know if everybody else in this group is, I shouldn't say. Which means that, you know, you can have, systems can exist as purely mental construct. I mean, think about if you've ever done any programming, or if you've thought up, a lullaby for your daughter, things like that. They can be a mental construct, you know, but they can also exist in the world, or they can do both, you know. And they can exist both in the natural and the human-made world. Many of the people that fall into this category don't consider boundary as an essential part of the system. And if you think about the more complex systems, or Dinesh likes to say systems of profound complexity, where do you draw the boundary sometimes? And the notion of a boundary gets, they call it paradox, the notion of a boundary where, you know, we're taught day one in systems engineering, where's the boundary of your system? Yet, you know, in the internet, where's the boundary of your system? You know, I mean, and these systems that are really system of systems and very complex systems, the boundary is very permeable, and it is very much around what you're trying to achieve to understand a system. And you can draw at multiple points. Some adherents, okay, so I'll talk about the next one, but the system boundary can always be discovered and refined. I already talked about that.
Next slide.
Hold on. Oh, the last point is important. A minority of the people in this category don't consider emergent properties to be defining characteristics of systems, which the notion of emergent properties, if you don't know this, is like if you have a conversation in the fellows group about emergent properties, you'll have a war. It sounds like bringing verification and validation up because we define them differently. You know, some people think emergent properties are things that you design into a system. Some people think that those are the emergent properties are things that happen that you didn't think about, that are the emergent because you didn't think about, you didn't plan for them to happen. Some people think they're both. Some people don't think that they're critical to a system, which is interesting. So, go ahead. The strong or extreme realists say that systems only exist in the real world. There is no such thing as systems that are conceptual. And there is a conundrum around the notion of conceptual systems because how do conceptual systems interrelate?
What's an example of conceptual?
A computer program that's not running, just a source code. Okay, and what's the emergent property of a definition of an algorithm or something?
This one fellow would say that unexecuted source code is not a system.
Right.
I agree.
A Mozart concert or sheets of music, that's a conceptual system.
Unexecuted?
Unexecuted. Okay. A model in SysML is a conceptual system, right? And there's
this one fellow says that a model is not a system.
It's not.
The model of a system is not a system.
Correct.
It's an abstraction of some characteristic of
It's a model.
something. Yeah.
Yeah. It's not a system.
And it might be useful.
Right. And some are useful.
But it is a system in that it's following a certain set of rules. A human, when reading it, will understand how the connectivity happens. Is it a system? I don't know any more than is a waterfall a system. I mean, these are the kinds of things that we ask ourselves in our when we're scratching this kind of topic.
Does it have a purpose?
Huh? Exactly. So the next one is the last worldview is on complex, viable, and living systems. And the key here is that people that are ascribed to this believe in much more strongly, and that it has to have more characteristics than the fact that it has a boundary or not, emergent properties or not, that the parts interact. And some of them are things like homeostasis, the ability to maintain a condition of equilibrium within its internal environment, even when faced with changes. So you think about the more complex systems that we're developing these days, we start to fall into this category. If your system is not able to maintain a condition of equilibrium going through an EMP storm, your system's going to die probably, Viability, the ability to survive in non-benign environments, that's similar kinds of concepts. When deployed into an operational environment, systems both change and adapt to their environment. Have dynamic and integrity limits. That's probably true of other systems, but a lot of people didn't think that it was a must. So these are people that believe these are must things for systems. Internal communications between parts, internal decision-making processes, resilience. This has some of the attributes that other people in other parts of this have, but these are specific to this particular one. Resilience, the ability to absorb and recover from major disruption. One of the concepts of resilience that you have to think about is the fact that resilient systems, think about yourself as a system. When you have gone through serious health issues or family kerfuffles, you're not the same when you come out of those as when you went in. So the notion of resilience doesn't mean that you're the same system coming out of those situations, but it does mean that you go on and you're able to rewrite the rules for whatever you're faced with now. So that's the concept of resilience. Adaptive control using internal feedback. So, I already did that one. Cohesive, the ability or characteristic of clustering as a group. And, we design systems on the principles of cohesion and coupling. So that's also what you see in nature. The characteristic of being whole and complete. Systems occur at multiple levels of integration, and new properties emerge at each level. So these are kinds of things that were in the survey, and different people answered them different ways, which was interesting. And we are putting together a survey now on systems engineering. It's a little bit more challenging, as you might imagine.
So, in the previous discussion, we said that there was one person who said that an unexecuted software code was not a system,
right.
which implies that everybody else thought it was. But how would you define that unexecuted software code in almost any of these terms?
Well, one of the things that and that's a good question. Let me think about that for a minute.
Or does that mean that people who ascribe to this worldview would not consider an unexecuted software code as a system?
Yeah, and that gets to that first point, complementary but uncorrelated with the three worldviews.
Okay. Oh, okay.
I'd say you could consider it a Bible.
Mm-hmm.
And then the other one is a mental, and that's one of the other worldviews.
Right.
Complementary.
Yeah, the mathematics-based one.
Or a mental construct.
Right. Okay, next slide. Now we're developing an integrated model. So with all of that, what are the fellows supposed to do? Right. Good. So, Bertalanffy is the general systems guy that is sort of the underpinning of systems science, and he includes two different types of systems: real systems and conceptual systems. And then a subset of the real systems are recognized systems. So there's real systems out there that we don't necessarily recognize or recognize as systems. Okay. Or maybe even bother to even think about them in those terms, because we're humans, just like all biological creatures, are opportunistic, and we look at the world for our own purposes, right? And so, anyway, so the notion of conceptual model. We also talk about the notion of that there is a correlation or correspondence relationship between, like what we talked about, SysML model and then an eventual realized system. And the idea of which one comes first doesn't really matter. There's just a correspondence between the two. And that's true for lots of different kinds of models that we create out in the world, even mathematical descriptions of algorithms or that eventually get put in code that eventually get into the system. So, so this is the underpinning of what we're doing. So the notion of synonyms that we saw in the literature, and you remember Miller was in the biological world or living systems, and then natural systems, Rosen, is that basically a real system can fall in these other categories. And then a synonym that was used was called abstract systems, which we use the term conceptual. Go ahead. So what about the other side? So when we think about real systems now, we went through and based on the literature and based on the stuff that we did with the 2025, we broke real systems into naturally occurring systems, hybrid of natural and artificial systems, which airplanes are artificial systems, and then in the hybrid category, artificially influenced versus artificially modified. So one of the things that we're realizing now is that humans create artificially influenced systems, most of the time without thinking about it, but in essence we do things to the environment or to the natural world that create these artificially influenced systems. And there's something that we have to then either address in some way down the way or think about. But what about conceptual systems? Go ahead. Keep going. So this is when we turn to some of the literature. A gentleman by the name of Popper in 1978, and he broke the world into three fundamental worldviews, or worlds. One is what we call the physical domain, which includes, things like objects, biological entities, events and processes and stuff like that. The next one, go ahead, is basically the individual mental domain. So what's going on in our heads, obviously, anything we realize as humans, we think about first, right? Because there's no way we can realize things unless we think about it first, right? And so we each have mental models, and if you've ever done any human-computer interface design, the biggest thing you're trying to do with your users is figure out how they're thinking about the system in order to be able to get them to think so you design it to where it's natural for them to think about it in the way that you intend them to think about it. And then the third world is that notion of objective knowledge, scientific cognitive tools, which then we went to Kent Lloyd, who is a New Mexican and very theoretical guy that used categorization theory to then break up the notion of shared conceptual domain, and go to the next one, and a formal domain. And so the categories, the way we broke up conceptual system, go to the next one. It's a notion of mental model, which, as I explained, is used quite frequently in human-computer design. Shared informal model, boxes and arrows, PowerPoint, and a shared formal model. So that's when you get into something that has more semantics and more understanding. Mathematics is a form of that. So those are all what we would consider conceptual systems.
Would you call an ontology a shared formal model?
Yes. As long as it holds water, as long as it's useful. As long as it's useful, yeah. Go ahead. And so this is our topology. This is what we're calling. This is what we've done with the term system. Looks like you've got a question over there.
Well, I'm sorry. I'm just looking at this, and you would use models to represent the system.
Correct.
Right. So it seems like these breakouts are orthogonal to each other. You've got types of systems on the one side, but now you've got types of models, which you use models to represent the system. And so the models would be orthogonal to that.
And probably a better way of saying it would be mental systems, but you're right. And that's one of the reasons why when we first presented this, and we actually have a member of our team, Dov Dory, anybody know Dov Dory, and OPM, he started trying to model this using basically a form of SysML, object process, familiar with OPM. And we put some of those up in front of the system science guys when they went wild. So it's not a true topology in the sense that there is not, it's somewhere between a taxonomy, a topology, and a category kind of thing, you know what I mean? So that's one of the problems with it. And the minute you formalize this, you get into trouble. And so that's one of the reasons why we're keeping the blue bubble instead. So, good point. Good point. And that's probably going to be brought up by other people. So I'll have to think about it for a bit on how I can answer it better. Go to the next one. So, kind of grand sum of these definitions. So, real system and conceptual system are systems. Real system exists in the physical world. Conceptual systems are a product of the human thought. Conceptual systems may be mental models, informal shared models, or formal shared models. Abstracted systems are conceptual systems that represent abstractions of real systems. Real systems may be naturally occurring, artificial, or hybrid. Hybrid systems may be artificially modified or artificially influenced. Hybrid systems and artificial systems may be intended or unintended. Recognized real systems are recognized to exist in the real world. They may be recognized by their structure, function, or behavior. And real systems can be characterized by their internal capacity for communication, decision-making, and adaptive control. What does that mean? They may be characterized. By some worldviews, they're characterized by those concepts. Real systems that share the characteristics of viable systems and living systems exhibit homeostasis, resilience, and the ability to cope with unforeseen circumstances. Think about complex systems. Autonomous systems, or a city full of autonomous systems is a good example to think about. Information systems are conceptual systems hosted in real systems. It has always driven me crazy when people say software systems. But software systems without hardware are not systems. But maybe I'm contradicting myself with my worldview, because software is real. We worry about software, right? But at the same time, is it a system without it running on hardware?
Unexecuted code.
Yeah.
Or is it a system without interacting with the human being?
Good point, too.
If the idea, what you said was, the conceptual system supposed to be a real system, then it would seem that the purpose of the software is to somehow stimulate or to communicate with a conceptual system, because as it stands, without that interaction with the human mind, all it is electrons running through wires.
Right.
So it isn't a conceptual system. The software until, I'm sorry, I think never mind.
Yeah. It's fun to think about these things, I think.
Right, well, to build up what you're saying.
Suspend our disbelief.
Go ahead.
Maybe we just need to suspend our disbelief.
Right.
Well, I was just thinking, I don't think an abstracted system can exist without a recognized system. Is that the conclusion you're trying to make? No?
Well, when it's abstract, then it's part of the conceptual system side. It's a model. Right.
Which may or may not be ultimately realized.
Okay, here's a what are those things that are called? They're given by the Buddhist masters to their students. Code? No. What is that thing? Anyway, Cohen. Is a system, if a deaf person writes just the most beautiful music in the world, but doesn't hear it get played, is it a system to him?
It was to Beethoven.
Yeah, I know. I was going to say Beethoven.
Anyway, so one of the things is, and this is hard because, we're taking a step into ground that is sacred for some people, and it's ground that's hard for some people because, we take for granted systems, you know what I mean? But when you start getting into thinking about systems engineering, we have to think about the systems that we're engineering, hopefully, right? And to take a larger perspective on that is important. Go ahead. So how do we map the worldviews into these different, this construct that we put together? I won't even call it typology. Go ahead. Click the next one. So worldview 1, believes that the abstracted system comes before the recognized system, and it's primarily a shared formal model. So that's the mathematicians, the computer scientists in the world. That's worldview 1.
So they would not believe in a natural model, a natural system.
No. Theoretically, that's true. Yeah. Go ahead. Worldview 2 is that there's really just conceptual systems because it's all in our brain. Worldview 3 is the moderate realist, which is the one that I told you, basically circles the whole bunch. Can you hit the button? And it just means that we believe there's real systems and there's conceptual systems, and there's some interplay between them, but not necessarily, It's the wishy-washy view. Worldview 4 is the strong or extreme realist, which is just basically systems exist in the real world, and that's it. And then the last one is the complex, viable, and living systems, which is primarily on the real system side systems that we recognize or don't recognize, but that we influence very directly. Go to the next one, and then I have one more slide after that next one. Well, I forgot. So let me just put this is sort of the summary. The conceptual model encompasses this conceptual model that we've developed. Maybe we should call it all something else. Encompasses more or less adequately all the belief systems and worldviews revealed by the fellows in the SSWG, and that we discovered in the literature. Conceptual model also spans all systems engineering activities we can imagine based on the 2025 vision. Grounded in widely recognized prior research, a single definition encompassing all types of systems in the conceptual model is possible, but it would be too vague to be useful. A family of definitions are better, and the best way of expressing these definitions is almost certainly natural language. That's what I was talking about before, because you start formalizing this and people start getting real excited. Go ahead. So, as a conclusion, which is just one more slide, we as a fellows team, and we've presented this material to our fellows group, our larger fellows group, and to the system science working group, and it'll be an evolving piece of work, but we believe that it's a good version 1. It accommodates all identified definitions and worldviews that we identified. We believe that it encompasses the scope of Vision 2025. Core definition is based on belief that emergence is primarily identifying characteristics of systems. In other words, when you bring parts together, there has to be a larger something that you're trying to achieve. Nature does that too. Finding a choice of words that avoids triggering unintended reactions from any important stakeholder we're trying to find as words. And then don't lose sight of a practitioner, just the average Joe trying to develop an airplane. We don't want to lose sight of them. So we're pretty much at a version 1 on this work, and we're moving on to systems engineering, definition for systems engineering. And we do find that the INCOSE definition is too narrow to accommodate the 2025, and that because of the wide variations, we've come up with 5 fundamentally different categories of world